Welcome everyone to the Critical Design Review presentation for Chanos, the Controlled Hydration Automated Nutrient Optimization System. Our team consists of me, Elliot D'Amato, a computer engineering major, Brian Erickson, a computer engineering major, Brandon James, an electrical engineering major, and Adrian Vergara, also an electrical engineering major.
Gardening can provide joy, relieve stress, and build confidence. However, busy work schedules can obstruct with this hobby. Disconnection from nature is correlated with reduced cognitive function and increased anxiety and depression. Our product will help nurture plants without constant human intervention. Unlike other existing products, our product has emphasized environmentally friendly features. The basic goals of our project include automatic hydration of the plant, the automatic drainage of the water runoff from the bottom of the soil, and ability of the user to adapt the system to a specific plant with unique hydration requirements. The advanced goals of our system are intended to make the product more eco-friendly. This entails reducing the environmental footprint of the design, minimizing energy consumption, and accommodating the use of sustainable energy sources. The objectives for our basic goals are the measurement of the soil moisture, the transport of water runoff from the pot to a separate container, and the design of a web application. The objectives for our advanced goals are the periodic sampling of the sensors, selection of lower voltage components, and reuse of filtered water runoff. The features of our product consist of a custom pot design, soil moisture sensor, light sensor, water level sensor, USB charging interface, lithium-ion batteries, and a web application. Three system specifications that we intend to demo are the web data update frequency, sensor sampling frequency, and power usage. Other system specifications are listed below. Component specifications are listed for various components, such as the water pump, solar panel, soil moisture, water level, and light sensors. A microcontroller was selected due to a lower energy consumption, cost, complexity, and size, and better built-in peripheral support when compared to microprocessors and FPGAs. Low energy consumption is important for our advanced goal of reducing the environmental footprint. Built-in support for peripheral devices is important for network communication and periodic sensor sampling. 5 popular low-power microcontrollers were investigated. One of our members already possessed ESP32 dev kits, so there's no cost listed on this slide. The ESP32 was selected due to built-in wireless support, low cost, and sufficient low-power modes. 4 main technologies for soil moisture measurement were investigated: capacitive, resistive, and time domain and frequency domain reflectometry. TDR and FDR were eliminated due to high design complexity and cost. Capacitive soil moisture sensor technology was selected over resistive due to advantages in accuracy, corrosive susceptibility, and calibration and maintenance, and little difference in design complexity. The soil moisture sensor product selected was DF Robot's Gravity Soil Moisture Sensor. This sensor was sold at the lowest cost. DF Robot also provides an open source schematic for the sensor, allowing for customization for our system.
Light sensors are used in our project to measure the sunlight our plant is receiving. This is important because it helps us adjust a watering schedule based on real conditions rather than being on a fixed timer. On this slide, we talk about 4 common types of light sensors and how they work. Light-dependent resistors change resistance with light intensity. It is relatively cheap but has a slow response time and low precision. Photodiodes generate a small current when photons hit it. It has a fast response time and high precision, but the signal is small and needs amplification. The phototransistor builds on a photodiode by adding built-in amplification so it produces a stronger signal with higher sensitivity. Finally, the digital lux sensor combines photodiodes with an ADC, so it directly outputs lux values over I2C or SPI. It's highly accurate, already calibrated, and covers a wide range of values, but it is the most expensive technology compared to others on the list. For our project, we decided to use the BH1750 as our primary light sensor. It communicates using the I2C interface, making it compatible with our ESP32. The sensor can measure a wide range of light intensity from just 1 lux all the way up to 65,000 lux. This makes it an ideal component for measuring both low and high light intensity conditions. It also has low power consumption, which makes it suitable for battery or solar powered systems. Overall, its simplicity, accuracy, and easy integration were the key reasons we selected the BH1750 for our system. Measuring water level is crucial for our system because it lets the user know when they have to refill the water tank. In this slide, we talk about 4 different methods of doing this. The float switch is a mechanical rising or falling component that triggers based on where you install it in a water tank. It's reliable and cheap, but only gives on and off information at a single point. The ultrasonic sensor emits sound waves and measures the reflection time to detect the distance to the water's surface. It's non-contact and works with many liquids, but can be affected by turbulence or water vapor. The pressure sensor measures hydrostatic pressure at the bottom of tank to calculate depth. It gives accurate continuous data, but requires calibration and is more expensive than the other sensors. Finally, the capacitive sensor detects changes in capacitance as water levels change. It has no moving parts, but is sensitive to the type of liquid used and dirt buildup. For our project, we decided to go with the horizontal float sensor. It works through a mechanical float that rises or falls with the water, triggering an internal read switch. This gives a binary signal to the microcontroller telling us whether there is water present or not. Because it mounts horizontally on the side of the tank, it's easy to install and maintain. It's also low cost and low power, making it perfect for our embedded system. For the purposes of our project, we really only need to know when the water gets past a certain point, making the float sensor a cheap but viable option for water level detection in our project. Another key design is the water pump, which will be supplying water to our plant. The peristaltic pump uses rollers to squeeze tubing and push liquid forward. It provides accurate flow control, can self-prime, and can run dry safely, but it has a low flow rate compared to other pumps. The centrifugal pump uses a spinning impeller to move liquid. It offers high flow and simple design, but it cannot self-prime and is not precise at low flow rates. The submersible pump has a motor that is directly inserted into the tank. It's quiet and good for moving large volumes, but is required to be waterproofed and is harder to maintain. For our pump, we chose the Adafruit peristaltic pump. It has a flow rate at around 100 milliliters per minute and runs 6 to 12 volts DC with an operating current of 200 to 300 milliamps. It's also self-priming, meaning it can draw water without needing to be pre-filled. This pump is commonly used in hydroponics, aquariums, beverage dispensing, and even medical and lab equipment, making it a great fit for our project by providing precise, controlled water flow.
For our batteries, we selected the Panasonic NCR 18650 lithium-ion cell in its protected version, which includes safeguards against overcharge, overdischarge, and short-circuit events. These cells are also widely used and highly reliable. For the solar panel, we selected the Voltaxic Systems P108 panel. It provides a stable voltage and output well matched for our charge control that we selected, as well as maintaining portability as its size meets the requirements that we wanted for our design. We wanted it to be portable and fit in a spot that is similar to where a plant would go, and this solar panel allows us to do that. For our buck converter, we selected the LM2596. We chose this over the other options, mostly for reliability. We had plenty of efficiency headroom, so we did not need to use a newer chip such as the TPS62162, and also provided more forgiving PCB layout. For our boost converter to power our pump, we selected the LM2577, which is in the same class as our previous regulator. Again, we did not need the extra efficiency headroom as our system overall uses very low power, and this chip is highly reliable, which meets our design requirements for reliability. For the solar charger, we chose the BQ24650. This controller allows us to use MPPT, which will allow us to charge a board even under non-ideal light conditions. This board also does not require any I2C programming. It can be programmed completely with resistors. Going on down to the last power component selection. This is going to be for USB charging. We selected the MP2672A IC. We made that selection for two key reasons. One, it provides load balancing while charging for our 2S battery pack design. It also has a separate system rail, which is nice to be able to potentially power a system off a USB if that is needed.
We chose wireless communication because the ESP32W room does not have built-in support for wired connections such as Ethernet. We chose Wi-Fi over Bluetooth because communication between the ESP32 and our web server is easier via Wi-Fi. We chose HTTP as our communication protocol because of our familiarity with it and its preponderance in web communication. Due to recommendation by Dr. Weeks and use within an official ESP32 dev kit schematic, we chose the CP2102 as our IC for USB UART conversion. The C/C++ programming languages were selected due to the support of the ESP IDF and Arduino frameworks. The Arduino IDE was selected due to the higher level of abstraction of the Arduino IDE methods and libraries compared to the ESP IDF framework.
Here were our choices for our web app software stack, aka our selection of our front-end, back-end, database, and platform softwares. The first software stack is the LAMP stack. This stack is known for simplicity and robustness, but it is too simple for most modern web development, and more advanced features are harder or even impossible to implement because of it, such as the advanced animations that can be created in more advanced front-end software. The second software stack is the MERN stack. Compared with the LAMP stack, it is much more advanced and flexible to work with. Working with MERN requires comfortability with JavaScript, but the reliance on JavaScript makes it easy to include dependencies that can make it easier to implement certain features, such as the back end of the stack, Express, which makes routing and responding to HTTP requests simple. However, the downside of MERN is that the database software used in MERN, MongoDB, is unstructured and harder to work with than other database softwares. This is where the software stack that we chose, PERN, comes in. It offers the advantages of the JavaScript-based MERN stack while also having a more robust database software that is easy to work with. And for that reason, we chose PERN.
For our overall hardware design, we have several subsystems functioning together for our system. Starting at the bottom here, we have our power system with a solar panel charging, feeding into a charge controller, which is then charging our battery. Our battery then supplies power to our regulators, which will then either drive the pump or drive our MCU and other various sensors that we have. Looking at the very top of this diagram, we have our water pump system, which comprises of a water pump and a water level sensor. And over to the left, we have a soil moisture sensors and a solar sensor, which is feeding information back to our MCU. Our MCU also has the ability to transmit and receive data from our external web server, which will allow the user to input parameters for how often to water the plant or to monitor light levels in order to ensure that our plant is being taken care of properly. Going over our two regulator boards for our system, we broke all of our ICs up into separate boards in order to be able to troubleshoot reliably, as well as our system did require a lot of flexibility as where to mount these boards. So having smaller separate boards allows us to be flexible on where we place them on our system. As we discussed earlier with the part selection, the layout on these two ICs was significantly more forgiving than other ICs, especially the more modern ones. Going on to the additional power boards that we have at the top, we have a fan out board, which allows us to send our power from our 2S pack to other various boards and regulators, as well as sensors. Bottom left, this is showing our charge controller for USB charging, and over to the right, we have the charge controller for the solar charging.
In this slide, we have our water level PCB. Its main purpose is to provide a signal path between the MCU and the horizontal water level sensor. All components in this PCB are meant to clean up the signal and prevent false readings from the sensor. In this slide, we have our BH1750 PCB. It utilizes two pull-up resistors, one for our ICL line and another for our SDA line. U1 is the BH1750 FVI chip, which will be used to calculate and transmit the lux values to our MCU. The rest of the components are used for clearing up the signal. This is our USB UART PCB. It takes packets from our computer, feeds it to the CP2102 chip located in the middle of the board, and then transmits the information to the MCU using two lines, namely TX, transmit, and RX, receive. To the left, we have our USB connection, and at the very top of our board, we have our voltage regulator, which allows us to power the MCU when connected to our computer.
The following is the microcontroller PCB design, including components for 12-volt pump control and LEDs. The following is the soil moisture sensor PCB design.
Here's our top-level MCU flowchart. You can see at the start we go through the initial setup to connect our pot to the internet. After that, we enter a more in-depth setup process for configuring static data, such as watering timers. Then, the pot essentially enters a loop where it waits for the timer interrupt, performs necessary actions such as watering the plant or creating water refill notification requests, and sends necessary data to our web server. Here is a more in-depth view of our pot's initialization process, with the main focus on how the pot connects to the internet. The two ways it can connect are if it already has information on the available network, which will cause it to attempt to reconnect to that network, or it will wait on the user to perform initial network setup. Here's our flowchart for our web app. It starts at the login/signup page, where it will then perform account validation or creation, depending on whether the user is signing in or creating a new account. After this, it will route the user to a dashboard page, where the user can then view their plants, add new plants, or view any notifications sent from their pots. Here is our software data organization. For the purposes of our web app, all data will be organized under users. Each user will have user-specific information, as well as a list of plants and a list of pots tied to their user account. The user class's information is mainly related to credentials and account authentication, while the plant class contains the static data used to set things like watering timers and moisture levels for the pot. The pot class will contain data that the pot will regularly update, such as its water level. For our web app design, we wanted to focus on ensuring that our app adhered to a standard set of design guidelines in order to ensure a consistent UI and UX across the web app. Our main concerns were adaptability, content-centric viewing, readability, and accessibility. For adaptability, we want to ensure that the design can adapt to a large number of screen sizes, such as phones, tablets, and monitors. For our content-centric view, we wish to have all related ideas viewable on one page with minimal use of tabs except in the case of separating different topics, such as our home and account pages as seen in our mock-up. For readability, we want to ensure that we define a color scheme with good contrast, and for accessibility, we want to focus on adding robust navigation options such as keyboard-only navigation or mouse-only navigation, to make it easier for people with disabilities that impact their ability to use certain devices on the app, as well as enforcing the use of alt text on images to improve the experience for visually impaired people. For the design of our web app server, we hope to implement an API using HTTP that enforces no direct communication between our client and any given pot. All should use the server as a middleman to ensure that the client is properly authenticated to interact with a given pot. The user authentication will be done using Google's OAuth services, which makes secure authentication of a user easy from both a user and developer standpoint.
Upon power up, the MCU checks if the Wi-Fi configuration data is already recorded in flash memory. If not, the user is prompted to submit a network SSID and password. After connecting to the client's Wi-Fi network, the user is also prompted to enter threshold values and initialize the sensors. After initialization, the sensors are sampled, during which the plant is watered if the soil moisture is too low. The MCU enters sleep mode and periodically wakes up until either a sensor threshold is changed by the user or after a watering time duration defined by the user. Standard deviation of about 1% was recorded for DF Robot's soil moisture sensor.
In this slide, we talk about our light sensor testing. After connecting our BH1750 to our ESP32 and ensuring proper wiring between our SDA and SCL line, we tested the sensor under 3 conditions, one with zero light, another with room light, and another with a flashlight. Our findings are presented in this table, which shows that our sensor was working fine under all 3 conditions. Testing our horizontal water level sensor involved connecting it to a GPIO pin or MCU, and using an LED that turned on and off to test if it worked. In the first photo, when the float sensor is up, the LED does not turn on. When the float sensor was down, the LED turns on. After testing this in a water container for our SD1 demo video, we verified that it worked great under different conditions.
For software testing, we tested to ensure that our ESP32 was capable of connecting to Wi-Fi and sending data in the form of JSON objects to our server. For this, we created programs for both our ESP32 and a local server running Express.js. We were able to receive the data on our server and display that data in a web browser. After testing to ensure we could receive data, we also tested to ensure that we could update the data on the ESP32. To do this, we sent a JSON object to our server containing the new data that we wanted on the ESP32. The server then sent data to the ESP32 using the IP of the ESP32 that was cached by our local server. We were then able to confirm that the ESP32 was sending us a JSON object containing the new information that we had sent to it.
For distribution, work is split up into 4 different roles. So starting at the top left, which is my section, I would be involved with PCB design and fabrication, primarily focusing on the solar power and other power delivery, anything to do with regulators or supplying the system with power. I'm also going to be assisting in the 3D printing of our project, and anything else to do with regulator design and helping troubleshoot any power-related issues. The bottom left, Adrian, he will be also involved PCB design, primarily focusing on the sensors and the MCU, and will also be assisting in the 3D printing design. The right-hand side over at Brian, he's responsible for the software design for the MCU, as well as supporting the MCU PCB design. He will also be assisting with the sensor design support on the software and hardware side, any of the web app support, and any smart home integration if we make some of our stretch goals. And finally, with Elliot, he is leading the software design for all aspects of our project, the MCU software and the sensor interface, as well as the web app development. Currently, where we stand for project progress is we have completed the research, the PCB and part sourcing is almost completed. Everything has been ordered, and we do have many of our boards assembled. We're going to be wrapping that up hopefully by the end of next week. We still need to do a lot of work as far as prototyping and testing. Overall, we're a little over halfway with the project completed. Some major milestones in the next coming weeks for us is verification and testing for the PCBs, integrating all the hardware systems together. Then once we have the hardware all integrated, integrating the software, doing our 3D printing for our enclosure, and then doing any final testing that we have.